Welcome to your deep dive. You sent us this PDF, this 1+300 Python Algorithms PDF,
Hmm.
and we're going to dive into it. I know we don't have to go through all 300 algorithms,
Mhm.
but we're going to focus on, like how the book is structured, maybe the data structures it highlights, and then dive into, some just really interesting algorithm examples that we pick out.
Yeah, I think that's a great approach. It's kind of like getting a sneak peek at a museum exhibit before you decide which pieces you really want to zoom in on.
Exactly. And so right from the get-go, the book mentions, it's for folks who are kind of new to the world of algorithms, but they already have, a bit of Python experience.
Yeah.
And it's all about getting you up to speed quickly and efficiently with, this whole world.
Yeah, and I think that starts with understanding what an algorithm actually is. So the book defines it as a sequence of instructions that process inputs, perform computations, and deliver outputs. Kind of like a recipe. You have your ingredients, you have the steps, and then you end up with a delicious dish.
Perfect. Okay, so now we've got that down. Let's talk about data structures. They're like the building blocks that algorithms use to organize and manipulate data. What are some of the key ones that are highlighted in this book?
Sure. Well, there are quite a few. But I think some of the superstars are arrays, stacks, queues, and trees. Each one has its own, unique properties and use cases. And it's really key to understanding them if you want to pick the right algorithm for a specific problem.
Let's start with arrays then. I mean, they seem pretty straightforward, like a numbered list.
Yeah.
But what kind of problems can they help us solve?
Yeah, well, one interesting example that the book brings up is finding the equilibrium index of an array. So that's the point where the sum of elements on the left side of the index equals the sum on the right. It's actually something that pops up in fields like physics and statistics, and it can be pretty handy to have an efficient algorithm to find it.
Interesting. And I see they also talk about, finding triplets in an array that add up to 0. Now, that sounds a bit more complex.
It is, and it kind of highlights how, the choice of data structure can actually impact an algorithm's efficiency. For this problem, you could brute force it, check every possible combination, but that would be incredibly slow. But by using a hash set, you can dramatically speed things up.
So the right data structure can be like a shortcut.
Exactly. Now moving on to stacks and queues.
Yeah, I always picture stacks like, a stack of plates. You can only add or remove from the top.
Yeah, that's a perfect analogy. It's that last in, first out kind of structure. Whereas queues are more like a line at a grocery store. First in, first out. They have applications in all sorts of things, like managing tasks, handling requests, even simulating real world scenarios.
And then there's trees, which seem a bit more intricate.
Yeah, so think of them like a family tree, branching out from a single root. They're great for representing hierarchical data. And they come in different flavors too, like binary trees, where each node has at most two children. AVL trees, which are self-balancing to make sure searching and insertion are efficient.
Okay, so we've talked about the book structure and some fundamental data structures. Let's get to the fun part now. Let's dive into some specific algorithm examples. One that really stood out to me was Floyd's cycle detection algorithm.
Hmm.
Now, this is used to find loops in linked lists, right?
It is, and it's quite clever how it does it. It uses two pointers. One's slow and one's fast, and they both kind of traverse the list. You can imagine them as a tortoise and a hare racing on a track. If there's a loop, eventually the hare is going to lap the tortoise, and that's how we know a cycle exists. And it's not just an analogy, it translates directly into the code.
Okay, so tortoise takes one step at a time, the hare two steps, and boom, when they meet, cycle detected.
Yeah.
That's pretty neat. What about K nearest neighbors, or KNN? I've heard this thrown around a lot in machine learning.
Yeah. K&N is all about finding the closest data points to a given query point. So you can imagine plotting data points on a graph, right? And K&N helps you answer questions like, what are the three closest data points to this new point? It's used in classification, recommendation systems, even facial recognition.
So it's like a popularity contest where the closest data points get to vote on what category a new point belongs to.
Exactly. But here's where things get tricky. As the number of dimensions in your data increases, the distances between points become less meaningful. It's called the curse of dimensionality. Imagine searching for a needle in a haystack. The bigger that haystack, the harder it is to find the needle.
So in a high-dimensional space, everything starts to look equally far apart.
Yeah, that's the challenge. And that's where efficient data structures like KD trees come in. They partition the space in a way that makes searching for nearest neighbors much faster, even in those high dimensions. It's like having a map to navigate that giant haystack.
Okay, now I really want to hear about the Chitnovsky algorithm. The book mentioned it's used to calculate digits of pi, but what makes it so special?
Well, the Chodnovsky algorithm is incredibly powerful because it can calculate the nth digit of pi without having to calculate any of the preceding digits. Like imagine you could jump straight to the millionth digit without having to figure out all the ones before it. It's mind-bogglingly efficient.
Wow, that's incredible. So we've got algorithms for finding cycles, classifying data, computing pi. What else does this book have in store?
Well, it wouldn't be complete without at least a mention of ciphers. And we start with a classic, the at-bash cipher.
Oh, that's the one where you reverse the alphabet, right? A becomes Z, B becomes Y. It's simple but effective.
It is. It's often used for fun or educational purposes, but, it illustrates the basic concept of substitution ciphers and how even simple algorithms can encrypt and decrypt messages.
Yeah, I remember playing around with that when I first started coding. It was a fun way to learn about cryptography.
Absolutely. Now let's jump to another intriguing algorithm. This one is simulated annealing, and it actually draws inspiration from a real-world process, the annealing of metal.
Ah, I've heard of that. It's heating and slowly cooling metal to remove defects, improve its structure. But how does that relate to algorithms?
Well, the simulated annealing algorithm kind of mimics this process to find optimal solutions to really complex problems. It starts with a high temperature, allowing for the exploitation of a wide range of possible solutions, and then it gradually cools down, focusing more and more on refining the best solution as it progresses.
So it's kind of like, it starts off exploring randomly, like hot metal with atoms bouncing around, and then slowly settles into a more ordered state, like the metal cooling and solidifying.
Yeah, that's a great way to visualize it. And this approach is especially useful for problems where there are many possible solutions, and finding the absolute best one would take forever.
And that's just a taste of what we've covered so far.
Yeah.
It's clear that this book is packed with a diverse set of tools for tackling all sorts of computational problems.
We've only just scratched the surface.
We've seen how data structures are like the foundation, like the building blocks for, these powerful algorithms. But let's move from like the blocks to actually like building something. And I'm really curious about this section on sorting algorithms, because this feels like such a fundamental task in computer science.
Oh, absolutely. Sorting is everywhere. And the book, covers a whole bunch of sorting algorithms, each with its own strengths and weaknesses. Some are simple and intuitive, like bubble sort, where you repeatedly compare adjacent elements and you swap them if they're in the wrong order. Kind of like organizing a bookshelf, right? You just keep moving books one position at a time until everything is in order.
Right. And I can see how that would work, but also it sounds like it would be really slow, especially if you have a lot of items.
Right. Yeah, exactly. And that's why you have more sophisticated algorithms like merge sort and quick sort. These employ a divide and conquer strategy. They break the problem into smaller, more manageable pieces, and then combine the sorted pieces back together. It's like, tackling a big project. You divide it up into smaller tasks and then merge the results.
So instead of like moving individual books around, you're sorting smaller stacks and then merging those stacks together.
Yeah, that's the gist of it. And these algorithms are much more efficient for those larger data sets. Now, the book also mentions some less common ones, like, have you heard of BOGO sort?
BOGO sort.
It's essentially just randomly shuffling the elements until they happen to be in order. Not exactly practical, but it highlights that there are many different ways to approach a problem, even if some are, well, much less efficient than others.
It's like throwing all your books up in the air and hoping they land in the right order. Not exactly my preferred method. But speaking of efficient searching, I remember being amazed by binary search. It's like a magic trick. Finding a specific element in a sorted array, but so quickly.
Yeah, the secret to binary search is that it takes advantage of that sorted nature of the array. With each step, it eliminates half of the remaining possibilities, so it quickly narrows down the search space. It's like looking for a word in a dictionary. You don't start from page 1, right? You open it up somewhere in the middle, and then keep having the remaining pages based on whether the word you're looking for comes before or after.
It's like a really strategic game of higher or lower.
Yeah.
I see the book mentions some other search algorithms too, like interpolation search and jump search. How do these differ from binary search?
Well, interpolation search you can think of as an enhanced version of binary search. It actually takes advantage of the distribution of values in the array to make more informed guesses about where that target element might be. Think of it again like searching a dictionary. You wouldn't just open it to the middle. You'd kind of use your knowledge of the alphabet to estimate where the word might be.
So it's using those context clues to make a more educated guess. What about jump search?
So jump search is a bit different. It divides the array into blocks and kind of jumps ahead to find the block that might contain the target element, and then it performs a linear search within that block. So it's a trade-off between the cost of jumping and the cost of searching linearly.
It's like browsing through a music library. You might jump to a certain genre or a certain artist,
Yeah.
and then browse through the albums just in that section.
Yeah, that's a great analogy. Now let's shift gears for a bit and talk about a really powerful technique called dynamic programming. It sounds kind of intimidating, but the core idea is pretty simple.
Okay, I'm all ears. What's dynamic programming all about?
So it's all about solving problems by breaking them down into smaller, overlapping subproblems, and then storing the solutions to those subproblems so you don't have to recompute them every time you encounter them. It's like building a tower, right? From the bottom up. You're using the solutions to the smaller problems as building blocks for the larger ones.
So instead of reinventing the wheel each time you're reusing solutions you've already found.
Exactly. And this can lead to huge efficiency gains. A classic example is calculating the Fibonacci sequence, where each number is the sum of the two preceding numbers. With dynamic programming, we can store those values of the Fibonacci numbers that we've already calculated, so we don't have to go back and redo it.
Makes sense. And I see the book also mentions like finding the longest common substring between two strings using dynamic programming. Can you give an example of how that might work in practice?
Sure. So imagine you have two sentences, like, the cat sat on the mat, and the dog sat on the rug. The longest common substring would be that phrase, sat on the, right? Dynamic programming helps us find this substring efficiently by breaking down the problem into smaller comparisons between parts of those sentences. It's used in all sorts of things, like DNA sequence analysis, even spell checking.
Oh, wow, that's really impressive. And I see they also touch upon this concept of Catalan numbers. What are those? And how do they relate to algorithms?
So Catalan numbers are the sequence of numbers that pop up in all sorts of unexpected places, like counting the number of possible binary trees, or figuring out how many ways you can arrange parentheses in a valid expression. They even appear in problems related to, like, triangulating polygons.
They sound like mathematical chameleons
Yeah.
appearing in all these different contexts.
They really are. And the fascinating thing is that we can calculate these numbers using, you guessed it, dynamic programming. The book gives a pretty clear explanation of how that works. It makes it easier to grasp the concept and apply it to actually solve those problems.
Now, switching gears a bit, let's talk about ciphers. They always add like an element of intrigue to the world of algorithms.
They do. The book covers a range of encryption and decryption techniques, starting with the classic Caesar cipher.
The Caesar cipher.
Yeah. It's a simple substitution cipher where each letter in the alphabet is shifted a certain number of positions. It's like, you're sending a secret message and you replace each letter with the letter that's 3 positions down the line.
So A becomes D, B becomes E, like that.
Exactly. A simple but effective way to encrypt messages, especially if you don't have a computer handy.
I remember using that as a kid to send secret messages to my friends. I felt like a spy. But I imagine there are more sophisticated ciphers out there.
Oh, for sure. And the book also goes into ciphers like the affine cipher, which uses modular arithmetic to kind of make it more difficult to crack than that simple Caesar cipher. They even revisit the @bash cipher, the one where you reverse the alphabet, as an example of a simple substitution cipher.
Right. And I see they also mention the RSA cipher, which I've heard is really important. What makes that one so special?
Well, RSA is one of the most widely used public key crypto systems, and its security really relies on the difficulty of factoring large prime numbers. It's like having a lock that can be locked by anyone with a public key, but it can only be unlocked by the person with the corresponding private key.
So anyone can send a secure message, but only the intended recipient can actually decrypt it.
Exactly. It makes it super valuable for secure communication and digital signatures. The book provides a good overview of how it works, explaining those concepts of public and private keys and their roles.
It's fascinating how these complex mathematical concepts can be translated into these algorithms that, actually safeguard our digital world.
Absolutely. Now let's shift our focus a bit to the foundation of many algorithms, mathematics. The book delves into a range of mathematical concepts and how they apply to algorithm design, starting with basic operations like addition, subtraction, multiplication, and division.
Okay, so that's fundamental. But I'm guessing algorithms require a bit more than just arithmetic, right?
Whoa, got it. The book goes beyond those basics, exploring things like exponentiation, logarithms, modular arithmetic. And they don't just present them in isolation, they actually show how these are used in specific algorithms.
Can you give me an example of how that might look? Like
Hmm.
how those concepts are actually translated into practical algorithms?
Sure. For example, they explain how binary exponentiation can be used. It utilizes powers of 2 to efficiently calculate those large exponents. It's like a shortcut for multiplication, allowing you to calculate 2 raised to the power of 10 without having to multiply 2 by itself 10
Oh,
times.
wow. That sounds pretty handy.
Mm.
What about prime numbers? I know they play a big role in cryptography.
Yeah, absolutely. The book includes a whole section on prime numbers and even introduces the concept of the greatest common divisor, or GCD, and something called the Euclidean algorithm for actually finding it.
The Euclidean algorithm, I feel like I've heard of that before, but I can't quite recall what it's all about.
Well, it's a classic algorithm for finding that greatest common divisor of two numbers, and it's incredibly efficient. It's a good reminder that many of these fundamental algorithms have been around for a long time, and they're still relevant today.
Yeah, it's amazing how these abstract mathematical concepts have such real-world applications in the algorithms that we use every day.
Now let's dive into another area where algorithms really shine: image processing.
Image processing. That sounds intriguing.
Yeah, the book explores various techniques for manipulating and analyzing images using, you guessed it, algorithms. It starts with basic operations like converting an image to grayscale, but it also goes into more complex things like blurring, sharpening, edge detection.
Right, those are all like really common effects in image editing software, but I never really thought about the algorithms behind them.
Oh, they're definitely there. And understanding those underlying algorithms can give you a much deeper appreciation for how those effects are achieved.
I'm especially curious about this section on error diffusion. What is that all about?
So, error diffusion is a technique used to represent an image with a limited number of colors, while trying to minimize the visual artifacts that can occur.
So it's kind of like compressing the image without losing too much quality.
Yeah, in a way, yes. So error diffusion algorithms work by distributing what we call the quantization error. That's the difference between the original pixel value and the quantized value. They distribute that to neighboring pixels. This helps create a much more visually pleasing result, even with a smaller color palette. The book covers several different error diffusion algorithms, each one with its own, characteristics and trade-offs.
And I see they even talk about more advanced techniques like Laplacian filtering and local binary pattern. What are those used for?
So Laplacian filtering is something that can actually enhance the edges in an image, makes them stand out more. It's like using a sharpening tool in an image editor. And local binary pattern, or LBP for short, it's a texture descriptor, often used in computer vision tasks. It's kind of like creating a fingerprint of the texture,
Hmm.
which can be useful for tasks like, recognizing an object or retrieving an image.
It's amazing how algorithms can extract so much information from images.
Yeah, and that's just a glimpse into the world of image processing. It's a huge field with applications in everything from medical imaging to self-driving cars.
Wow, we've covered so much ground already. It's incredible how this book manages to pack so much algorithmic knowledge into one resource.
We're not done yet. In the final part of our deep dive, we're going to explore even more fascinating algorithms and leave you with some thought-provoking questions to ponder. So stay with us.
We've explored so many fascinating algorithms already, from sorting and searching to ciphers and image processing. It's amazing to see how these computational tools are kind of woven into so many different fields. But there's one area that I'm particularly excited to delve into, and that's machine learning. It seems like it's everywhere these days.
It really is. I mean, machine learning is revolutionizing so many things, from
Mm.
healthcare to finance, even entertainment. And at its core, it's all about these algorithms that can actually learn from data and make predictions or decisions.
So instead of, like explicitly programming a computer to do something, we're giving it data and letting it kind of figure things out on its own.
That's the basic idea, yeah. And this book, gives us a taste of some of those fundamental machine learning algorithms, starting with the a priori algorithm, which is used for association rule mining. Think of it like, analyzing shopping cart data to discover relationships between items that are frequently purchased together.
Like the classic example, people who buy diapers also tend to buy beer.
Exactly, you got it. It's all about finding those hidden patterns and associations in the data. The book also introduces more advanced concepts like automatic differentiation, which might sound a bit intimidating, but it's actually super useful.
Automatic differentiation, what is that all about?
Well, in a lot of machine learning algorithms, we need to calculate derivatives of functions. It's a bit of calculus, but essentially derivatives tell us how a function changes as its input changes.
Okay. I vaguely remember derivatives from calculus, but why are they so important in machine learning?
Well, derivatives are crucial for optimization. A lot of machine learning algorithms work by finding like the best set of parameters. And derivatives kind of help guide that search process. So automatic differentiation allows us to actually calculate these derivatives automatically without having to do it by hand, which can be super tedious and error prone.
So it's like having a calculator for derivatives, a huge time saver. What other machine learning algorithms are highlighted in this book?
It covers a good range, including decision trees, which are kind of like flowcharts that help us classify or predict outcomes based on a series of decisions. It also goes into dimensionality reduction techniques like principal component analysis or PCA.
PCA, yeah, I've heard of that before. It's like simplifying a complex data set without losing too much information, right?
Yeah, that's a great way to put it. It's like finding the most important features or patterns in the data.
Yeah.
And they also touch upon k-means clustering, which groups data points into clusters based on their similarity.
So it's kind of like sorting your socks, putting all the similar ones together.
Exactly. Each cluster represents a group of data points that share certain characteristics. It's used for all sorts of things, from customer segmentation to image analysis.
Wow, this is really just a peek into the world of machine learning. But it's already clear how algorithms are kind of driving these powerful techniques.
Yeah, and this is really just the tip of the iceberg. There's a whole universe of machine learning algorithms out there, constantly evolving and pushing the boundaries of what's possible with data.
Speaking of pushing boundaries, let's move on to one final area that I think is essential for understanding how algorithms are shaping our world, and that is graphs.
Ah, yes, graphs. Incredibly versatile. I mean, they can represent relationships between entities. Think about social networks, where nodes represent people and edges represent connections between them, or maps, where nodes represent locations and edges represent the roads that connect them.
So they're like visual representations of connections and pathways.
Exactly. And the book introduces some of those fundamental graph algorithms, starting with breadth-first search, or BFS, and depth-first search, or DFS. These are essential for like traversing or searching those graphs.
I remember those from my computer science classes. BFS explores the graph layer by layer, like ripples spreading out from a stone dropped in a pond, while DFS dives deep into each branch before backtracking.
Perfect analogy. They also cover algorithms for finding the shortest path between two nodes, like Dijkstra's algorithm, or A, which is commonly used in GPS navigation systems.
It's amazing to think those algorithms are working behind the scenes, guiding us to our destinations.
And they even touch upon ant colony optimization, which is this nature-inspired algorithm that mimics the foraging behavior of ants to find optimal solutions. It's a really cool example of how we can draw inspiration from the natural world to actually design effective algorithms.
So, we've journeyed through this incredible collection of Python algorithms, exploring this vast landscape of computational tools and techniques.
We've covered it all, from sorting and searching to machine learning and graph algorithms, really highlighting how these tools are used to solve problems across a huge range of fields.
Yeah, it's been an eye-opening experience, to say the least. But what does this all mean for our listener, who's been on this deep dive with us? What's the key takeaway here?
Well, the key takeaway is that algorithms really are the building blocks of our digital world. Understanding them is essential for anyone who wants to not just use technology, but understand how it works and how to shape its future.
This book has provided such a fantastic overview of this diverse world of algorithms, but it's really just the beginning.
It is. It's like we've given you a taste of different cuisines from around the world, and now you have the knowledge and the tools to explore each one in more depth.
And as you continue that exploration of algorithms, I want you to consider this. Yeah. With so many algorithms out there, how do you choose the right one for a specific problem?
That's the question, isn't it? And the answer often depends on the specific context. Factors like efficiency, the size of the data, the nature of the problem itself, even the available computing resources. All of that can influence your choice.
It's like having a toolbox full of tools, and you need to know which tool is best for the job.
Right. And the more you learn about algorithms, the better you'll get at choosing the right tool for the job. And that's where the real fun begins.
So keep learning, keep experimenting, keep pushing those boundaries of what's possible with algorithms. Until next time.